Welcome back. How we doing, my brave little toasters? We are going to go over chapter 4 today. Everybody's favorite. What is chapter 4? Rational functions, of course. Of course. Rational functiones. Boom. There we go. So these rational, just one more time for the kids at home. This means fractions. And I know. Fractions, how do you spell fractions? Fractions are one of your 3 greatest fears. No need to list them off. I already have them memorized. You've told me 1,000 times. But we're going to go over rational functions. I think most of this unit is very straightforward. And maybe there's 1 or 2 things we get a little hung up on. But 4.5 was everyone's favorite unit lesson, which was word problems. So we're probably going to spend a good deal of this video futzing around with some word problems at the end, but you'll be fine. You'll live. Don't worry. You've done this once already. You've clearly lived through it. So let's get going. So the first thing we need to know is, how do I find the root of a rational function? Don't mind that. That's just my tablet clicking into place there. So if we want to find a root, there's 2 things we need to do. We need to find the roots, of course, that's what the problem asks. But the other thing we have to do is we have to find the restrictions. Because sometimes, even if it looks like it's going to be a root, it's one of those values that's illegal anyway, so it can't happen, right? It's like when your mom says, well, what are you going to do with your friends? And you say, oh, well, we're just going to go smoke a doobie. And your mom goes, but that's illegal. It's a restricted value. You're not allowed to do that activity. So you got to change your plans, right? So it's not a root anymore. You throw it away. Oops, sorry, guys. My mom says I'm not allowed to. She says smoking's bad for your health. So you throw it away. So let's start with, how do I find the roots? For these functions, let's make it a function. There you go. Now it's a function. What a root means is that our graph touches the x-axis. So if there's our graph, our roots would be here, here, and here. And what's special about these 3 points is that they are on the x-axis. That means they're going to have ordered pairs like -2, 0. -1, 0, and maybe 1, 0. The important pattern you're supposed to recognize here is that the y value is always 0. So what we're looking for is what makes our function equal 0. And the way we're going to do that is we want the top to be 0. So 0 divided by anything, right? 0 divided by 12. Well, if you take 0 things and put it in 12 groups, every group has 0 things in it, so it's still 0. So the trick here is set the top equal to 0. When we do that, we're going to try and find the roots, and the way you do that is by factoring. So basically all you're going to do is factor the top, and then you set the roots equal to 0, or set the factors. And when we say factors, we're talking about binomials. Okay. So step 1, let's factor the top. The first thing we notice is that there is an x in all of these. So let's factor out our GCF of x. So we have x, and we need to just decrease these by 1. So this will be x squared minus 2x minus 15. Let's go ahead and move this down here. Okay. All right, so we factored the top a little bit, but we could factor it more because this thing right here, we could do simple factoring on. So I'm going to bring out that GCF of x that I already factored out. Now I need 2 numbers that multiply to -15 and add up to -2. So that's going to be x minus 5 and x plus 3. So -5 times 3 is -15, and -5 plus 3 is -2. All right. I'm going to just bring this stuff down so we have it. So x plus 3 and x plus 5. Almost there. So if we set each of these three numerators equal to 0, those will be our roots. So x equals 0, x minus 5 equals 0, and x plus 3 equals 0. Let's try and move that bottom one down a little bit. Huh? Shucks. It's never that easy. Okay, so this one is already solved. X equals 0 as a root. If we add 5 here to move the 5 over, we get x equals 5. That's a root. Subtract 3 here. X equals negative 3. So those are our three roots. X equals 0, x equals 5, and x equals negative 3. But, and this is a big but, this is like, no, that's vulgar. I can't say that. You guys are kids. We need to find our restrictions because some of these might be things our mom's going to say, no, you're not allowed to do that, right? She said, no, you can't smoke cigarettes with your friends. Those are bad. So the way we find restrictions is we do the exact same thing we just did here to the denominator. Because if the denominator equals 0, oh, I'm dividing by 0. This is like the worst thing you could ever do. This is worse than telling your grandma that you don't like her fried rice or whatever, right? This is like telling your mom that you don't appreciate all the stuff she does for you. This is like when your mom drops you off at your friend's house and you don't say thank you. It's worse than that. So what we do is we set the denominator terms equal to 0, solve for x, and then we say x doesn't equal those numbers, and those are our restrictions. So if we have x plus 3 equals 0, subtract 3. So we have x does not equal negative 3. That's a restricted value, and it's bad and you're not allowed to use it. X plus 5 equals 0. Subtract 5 on both sides. X equals negative 5, but it doesn't equal. X does not equal negative 5. It's a restricted value. So now we just compare these to our roots. X equals 0, not restricted. X equals 5. Here's negative 5, but those are different numbers. Negative 5 is way over here on the number line. There's 0. There's 5. They're different numbers, so don't worry about that. X equals negative 3, but x can equal negative 3. So this root is not a root because it's a restriction. Cool? All right. Nice. You guys did it. You lived through the first example. All right. We're going to use this idea for restrictions a couple more times because they help us find some other things, like the domain. So if it asks us for the domain of a rational function, polynomials, gosh, bless America. All right. If we have a rational function and we want to know the domain of this thing, polynomials have a domain of all real numbers, negative infinity to infinity. But because of this denominator right here, there are restricted values that our mom has said we're not allowed to use, we're not allowed to touch, we can't go over to their house, no, they can't spend the night. So we have to take those out of our domain. So the first thing we need to do is factor the bottom of this and then set those factors equal to 0 to find the restricted values. So the top here is not really important for domain. I made it extra boring. It's just a 3 so that you're not tempted to do anything with it. So we're going to factor the bottom. Let's start by taking out the GCF of x. So we have x times x squared minus 9x minus 36. And then we can do simple factoring on this trinomial right here. So we need two numbers that multiply to negative 36 and add to negative 9. Luckily, I wrote the question, so I know the answer already. It's x minus 12 times x plus 3. Now we have to set these all equal to 0, including the x, to get our 3 restrictions. Pro tip, whatever that exponent is, that's how many restrictions you're going to have, unless they're repeated, of course. So x does not equal 0. That's our first restriction. X minus 12 does not equal 0. And then x plus 3 does not equal 0. So we already have a restriction here. Let's find these two. So we add 12. So x does not equal 12. And then subtract 3. So x does not equal negative 3. So if we're thinking about our domain as a number line, right now our number line is full. It's complete. There are no holes in it. We can use everything. But we just found out 0 is a restricted value. So we need to go to 0. Right, there's 0. And we need to put a hole in it. Then we need to go to negative 3. And we need to put a hole in it. Then we need to go to 12. And we need to put a hole in it. So what that's going to do is it's going to cut this into chunks. So we need to say less than negative 3. Then we need to say from negative 3 to 0. Then we need to say from 0 to 12. And then we need to say from 12 to infinity. Those are the chunks that we're going to have. So we can see 1, 2, 3, 4. This one domain interval is going to be cut up into 4 separate intervals. So let's move this over a little bit so that we have some room to work. Okay. All right. So the first interval we need is everything smaller than negative 3. So our domain, it's still going to start at negative infinity. This thing can go as far down as it wants. There's no more interruptions. So it's going to go from negative infinity up to negative 3. And because we're putting a hole here, we are not including negative 3, so we put a parenthesis. Now to connect this next section right there, we need to put a union. This section starts at negative 3. So we're going to start at negative 3. You can see how these two numbers match. That should pretty much always happen for rational functions when we're writing our domain. It goes from negative 3 to 0. Close that parenthesis because, again, it's a hole and we're not including the value. Union again because we're adding another section now. This one goes from 0 to 12. Union. And then this one goes from 12 to infinity. And infinity gets a parenthesis because it's not a real number. It's a made-up symbol so that we kind of can represent forever. But you can't get to forever, so you don't include it. And it's that easy. So you just find your restrictions, and then you cut up your domain, putting holes where the restrictions are, and then writing the domain out in interval notation is pretty easy from there. All right. Now we need to talk about asymptotes. Make sure you watch your language. Don't say this word around your mother because she'll get upset. So a vertical asymptote happens when the function is undefined. And what undefined in math means is it means you have a number divided by 0. This is the most cardinal sin, right? If there were 10 commandments of math, this would be the first 9. Thou shalt not divide by 0. So to figure out where we divide by 0, you're just finding your restrictions. So again, we go factor this thing and set it equal to 0. So this will factor to x minus 6 times x plus 1. And let's just double check our math. Negative 6 times 1 is 6. Oops, I made a mistake. I did that on purpose to show you that it's not always the right one. You have to check your math. So because that didn't work, we have to find a new way. We need two numbers that multiply to positive 6, and we need those same two numbers to add up to negative 5. So this is x minus 2, x minus 3. So negative 2 times negative 3, yeah, that's positive 6. And then negative 2 minus 3, that's negative 5. Set these equal to 0. So we have x minus 2 equals 0, x minus 3 equals 0. So x equals 2, x equals 3. And technically the restrictions, so it's not allowed to equal those. But if we look at our graph will look like this. Let's do 1, 2, 3. So it'll look something like this, maybe. It's not allowed to equal 2, and it's not allowed to equal 3. So let's do maybe one of those, and then one of these. Okay. So our graph misses these, but we don't want to know it's not allowed to be 2. What we want to know is what is the equation of this vertical line, and it's x equals 2 and x equals 3. So these are restrictions because it's saying x is not allowed to be that, meaning don't plug these numbers into that. Whoops, I dropped my pen there. Sorry, you guys. Don't plug them into this equation. But when we ask what are the vertical asymptotes, we're asking what is the equation of that invisible line that our graph is avoiding. So then it's x does equal that number, x does equal the other number. Okay. Remember, vertical lines are always x equals a number, because if you look at all your ordered pairs on this line, it's 2, 0, 2, 1, 2, 3, or 2, 2, excuse me. I know how to count. So because all of your ordered pairs have the same x value, we say x equals that number. Okay. So again, to find vertical asymptotes, you're finding your restrictions, and that's x equals the restricted number. Okay. For horizontal asymptotes, these are, if we look at a graph, these are going to be those invisible horizontal lines that your graph kind of levels off to. So for rational functions, the ends always kind of converge towards some normal value, like 2 or 3 or a half or something. So we want to know what is the equation of this invisible horizontal line that our graph is getting really close to. So it is not setting the top equal to 0. That was how we found our roots of the function where it crosses the x-axis. To find the horizontal asymptote, what we want to ask is what does the fraction reduce to if you plug in really big numbers, right? This is very similar to end behavior. So there are 2 cases we want to worry about. The first case is going to be top and bottom have an equal degree, meaning their largest exponents are the same number. So let's look at this first example here. Sorry, let me erase this graph. All right. So we want to know what's the degree of the top of this. You could FOIL this whole thing out, but it's really easy to tell the degree by just counting the number of x's in these terms. 1, 2. So if I multiply these together, 2x times x, you're going to get 2x squared. There's the degree. So if you just count the x's in the top, the degree will be however many there are. So if you had like maybe another one like x minus 2, that would change this to a third degree because now there's a third x in the top. Okay. So the top is going to be x squared because there are 2 x's. The bottom is also x squared. So if we plug in really big numbers, we're going to have some extra stuff after the squared, and we've got some extra stuff after the squared. But exponents get a lot bigger faster than other math operations. So if you plug in like a billion, let me see if I can remember how to write a billion. Yeah, 1,000, million, billion, yeah. Then these other terms are not going to be very big, right? 5 times a billion will be 5 billion. But a billion squared is this with 9 more zeros on it. It's so much bigger. It's a billion times bigger, right? So it kind of overpowers it. So what we want to look for once we've determined that our coefficient, or rather our degrees, are equal. So let's say this is 2x squared plus some stuff, and then we have x squared plus 5x minus 14. All we care about is the ratio of those leading coefficients. Your horizontal asymptote is going to be y equals this ratio. So 2 over 1, and of course reduce that because we're not lazy. So y equals 2 is the equation of your horizontal asymptote. That's for them having the same degree. The second case that we're going to worry about for this class is the bottom is greater than the top degree. So this just means that the exponent on the bottom is a bigger number than the exponent on the top. And this one is even easier than this one. This is actually the harder case over here. If the bottom is bigger, then the bottom just overpowers the top. And what happens when you take a small number and then you divide it by a big number? If you type this into a calculator and turn it into a decimal, it's like point and then a whole bunch of zeros. I think that. I don't know. You could check. This is super tiny. This is really close to being, this is almost 0. So if we continue to plug in bigger numbers, it would get even closer. So anytime the bottom exponent is bigger than the top exponent, our horizontal asymptote is y equals 0. All right, we're done with asymptotes, calculating them. You're also going to have a couple graphs where they say, what are the asymptotes? And I think this is, I don't know, I think this is insultingly easy. But then again, studies show math teachers don't know what they're talking about. So I won't say that because it'll make you guys feel bad. But you know how I feel. You know how I feel about those graphs. So let's just write down all the asymptotes from this graph. So we have this pseudo-invisible line. It's not really invisible because it's dashed, but we'll pretend we can't see it, right? So we want to know, what's the equation of this invisible line? So because it's horizontal, this is going to be a y equals equation because all the y values are the same. This is 0, 1, 1, 1, 2, 1. All the y values are 1. So this is y equals 1. Then we want to know what is the equation of this vertical line. So because it's vertical, that's going to be x equals a number. And we're crossing the x-axis at 1, so it's x equals 1. And then we want to know the equation of this vertical line. Because it's vertical, it's x equals, and it crosses the x-axis at 4. There you go, you're done. You did it. You looked at a graph and you wrote down the asymptotes. I'm proud of you. Go hang this on the fridge so your mom can be proud of you too. I know. Now we're at the dreaded word problem. Ooh, that was my water bottle. Don't mind that one. Sorry. I was a bit parched. So we have a word problem. Let me just refresh your memories on something real quick. There's an equation in math, and you already know it. It's y equals mx plus b. Let's talk about this equation really quick, and then we'll do this word problem. So in this equation, m is your slope. Sometimes people call this a rate. B is your y-intercept, but on all of these word problems you're going to deal with, you don't have any starting values. You start with no cars washed, or no yards cleaned, or no dishes done. You haven't done anything yet, so B is just 0. And then x is your independent variable. Usually you're doing something and it takes you some amount of time. So usually this x is going to be your time. And then y will be the total number of things you do. So there's a maybe more concrete way we can discuss this equation. total equals rate times time. So what we're going to try and do is we're trying to make some rates and then probably solve for the time. How long would it take? That's time. So we're looking for the time, and they're going to give us a total amount of things to do. So they're going to give us a total. We have to figure out the rate, and then we can use this equation to solve for our time. So let's go look at this. It says Kevin and Marissa both work for a car detailing company, meaning you bring your car to them, they like vacuum the inside, they wipe it down with those little wet wipes, they get all the dog hair out of it, they throw away all the McDonald's cups you got laying in the passenger seat, and then they'll like wax the outside so it shines really nice, right? They're going to detail it so that you look fly for the honeys when you pick them up on a date, or what do girls call boys? Not honeys, right? You wouldn't be like, yo, I'm gonna go pick up my honey Jose, or maybe you would, I don't know, but regardless, boys or girls, you're gonna go pick up your boyfriend or girlfriend for a hot date, so you gotta get your car looking fresh. Okay, so you take it to Kevin and Marissa and they clean up your car. Kevin can detail 5 cars an hour, and Marissa works 1.4 times faster than Kevin. She's been on the job a little longer, so she's a little quicker, you know. We want to know how long would it take both of them together. So they're both on shift today. They come into the shop. They each get their little bay with their wipes and their vacuums and stuff. How long is it going to take them to do 36 cars? So let's go find our rates. They tell us Kevin's rate. It says Kevin can do 5 cars in an hour. So we'll put K for Kevin's rate. You want to put the number of things you're doing on the top, and then you want to put the time unit on the bottom always. So we can do 5 cars over, and this is the English word for 1. I have an. When do you use an and when do you use a? Either way, it means 1. So in 1 hour. And then we could make this look a little bit nicer because 5 over 1 is just 5. So this is 5 cars per hour. All right, so Kevin can do 5 cars per hour. Then it says Marissa works 1.4 times faster than Kevin. So Marissa equals Kevin's rate times 1.4. She's 1.4 times faster than him. So you can either leave it as an equation, or you could just plug in the 5 to K and then multiply by 1.4. So that you don't have to guess, I'll just tell you it's 7 cars per hour. Now we want to know how long would it take them to detail 36 cars. Because they are both working together in conjunction, we add their rates together to get our total rate. Total rate equals Kevin's rate plus Marissa's rate. And this is not 100% true for everything in the whole world. Like if you're washing dishes together and you work at Burger King, there's not a whole second sink where you can just move some of the dishes and both do the entire job yourself. Usually it's one person carries the dishes over, and then one person kind of washes them, and then they wait, and then you can't both just work full speed together. But we'll pretend they can. They both have their own car bay, right? So we just add their rates together. So now we're going to plug in our total rate into this equation, and we know we're trying to do a total of 36 cars. So we have 36 cars equals Kevin's rate plus Marissa's rate times T. And we're looking for this T. How much time does it take them to do all those cars? So we're going to plug in these numbers. We have 36 equals 5 plus 7 times T. 5 plus 7 is 12. So this is 12 times T. Divide both sides by 12. So T equals 3 And then this is a unit of time. So what are our units for time? Minutes? Oh, we're doing it in hours. So this is going to take them 3 hours to do 36 cars. All right. I know I made that look easy, but I've been studying, you know. I've been doing this a long time. This is like watching Arnold Schwarzenegger work out. You're going to be like, wow, he makes 400 pounds look really light. It's because I'm the Arnold Schwarzenegger of math. But you guys got to go hit the gym. You got to do your own mental deadlifts and stuff. You got to go pick up a couple cars yourselves. So go ahead, hop back in the WebEx. You're going to try your assignment, and I'll be there to hold your hand. I'll spot you, bro. Don't worry. I won't let you crush yourself to death with word problems.